Okay, our next speaker is Chen Zhang. So he's at National Tsinghua University, and he's going to tell us about hyper-subprime CAN, archive and photoseed. Please.
Good afternoon, everyone. I'm Simon Ho from National Tsinghua University. So my supervisor is Professor Tomozuku Goto, so you may already listen to his talk on Monday about NEP data and dumpling. So unfortunately, I'm not talking about dumpling in this talk, but I will focus on photometric redshifts that he mentioned in his talk. And to be frank, I don't have any fancy animation from simulation, but I want to share you some how did I compute this photoseed, which is quite important to our group's other research. So I hope you enjoy this talk. And I changed my talk a little bit, so don't be confused. I think Thomas already talked about this, so I want you to recall your memory. So our data is mainly come from a space-based infrared telescope called ASIAA. The biggest advantage of ASIAA is that it has its 9 bands photometry in near to mid-infrared wavelengths, and from around 2 micron to 24 micron. And there is no gap in between the filters. Compared with Spitzer and maybe WISE, there are gaps in between the filters. So in principle, ASIAA can detect more sources, infrared sources, that Spitzer and WISE couldn't do due to these gaps. I mean, gap may be a good brand, but we don't want gap in infrared astronomy. So in 2012, Kim et al. By Songjin Kim, one of our collaborators, he published a paper about infrared sources from ASIAA data on the NEP wide field survey. Unfortunately, we didn't have enough optical data for the NEP wide field survey. So here you can see this gray region is the NEP deep field survey, and this large green coverage is the NEP wide field survey, and this red rectangle is the coverage of CFHT mega-cam optical data. You can see that CFHT only covers the whole NEP deep field survey, but it didn't cover the whole NEP wide field survey. And also we need deeper optical data to get better photoseed. So thanks to Tomo-san, he wrote a proposal to HSC in 2014. So he asked for observation of HSC on the ASIAA NEP wide field. So finally we get deep optical data, then I can do photoseed later on. Just in case you don't know how exciting and how powerful to combine ASIAA data and HSC data all together, I will elaborate by a cartoon. I don't know if you know Dragon Ball, but actually I'm not a Dragon Ball generation. So if I'm wrong, please forgive me. So in Dragon Ball, there's a scene called fusion. So 2 of the characters in Dragon Ball, they just do something like this, and they will combine together and become something like Super Saiyan, I don't know, just some powerful character you imagine. So let's imagine we have 2 more characters, which is HSC data and ASIAA data, and they undergo fusion and become a very super powerful NEP wide field data. So here we have 4 circles here. These are the new NEP HSC deep field data we got in the NEP wide field survey. And the red circles here is the NEP whole wide field area. So now I can finally do my job to estimate photometric redshift for this region. And moreover, Songjin Kim I mentioned before, he also merged our HSC data, ASIAA data with other telescopes, something like WISE, Spitzer, Herschel, Madanak, CFHT, and even etc., etc. So we have a very large bandwidth schedule, around 40 bands maybe. And the sources in total are around 92,000 here. And the sources in total with SPECS is around 2,000. And you may ask me why we need so many bands, so many filters for photo C. But I will tell you that even they are called R, HSCR, and CVHTR, they are so-called R band data, but actually their effective wavelength is quite different, not quite different. They are slightly different in their effective wavelength. So in order to compute a very good photo C, we need as much as possible, as many filters as possible. So we just get as many filters as possible. And also, it's very crucial to have something like U band from CVHT because there is some boundary breaking low redshifts in the SCD. And also, we need near-infrared data for higher redshifts or galaxies. So it's very important to have many filters. So eventually, we have 25 bands from night and dark to WISE. And these bands are essential for our photo C research. And the code I use to run photo C is called LUFA. And not to confuse with this LUFA in Kaita. This is just a SED fitting code which is computed by French. And LUFA in French is actually lighthouse in French. So that's why my front page is a lighthouse. And this code is very powerful and I use it to compute photo C. And the first thing I do in my research is that there are some special cases in my sources. So I need to set up some context for them in order to compute a better photo C. So the first case is that in HSC, so HSC is not perfect. So sometimes HSC is not reliable. For example, for this figure, this shows the SCD fitting of one of the source. You can see that Subaru HSC data, they are very faint compared with the similar wavelength in Madanach data. And for this graph, it's similar. So Subaru data is quite faint compared with MegaCam data. So in these cases, we cannot rely on Subaru HSC data. And we also check the images of these sources. We can see that this is probably due to the multi-detection of HSC data or saturation of HSC data. So here I show some HSC optical images and some Akari infrared images. You can see that these cyan circles are actually the detection in HSC of this bright source. So in this pipeline, the flux from this source is divided to many circles. So one of these circles are matched with our Akari data, which is shown by the green circle. So that's why this HSC flux is lower than the Akari flux a lot. Not Akari source, I mean MegaCam flux a lot. And how to fix this, we design some criteria to exclude this kind of bad HSC data. So we plot 3 sigma contour in this HSR minus Madanach R versus Madanach R plotting. So we decided to use Madanach optical data instead of HSC data for these 3 sigma outliers. So same thing we do to the MegaCam data. We use MegaCam data instead of HSC data for these 3 sigma outliers. And our result improved a little bit. And before going to the results, I want to define some symbols in my plotting. So sigma here is actually photo C deviation. So it is a normalized median absolute deviation defined by this formula. And eta is the outlier fraction. I define outliers as delta C divided by 1 plus spec C larger than 0.15 or smaller than minus 0.15. And n gal is the number of included galaxies. Basically, these symbols, this value, smaller the better. The first thing I do to get the best photo C is to compare different temperature models. So this time the control variables I chose is 25 bands I just mentioned. So I tried 6 different kinds of template models from Cosmos to CWW. You can see that the best one is Cosmos in my case. And the second thing I do to compare is I compare different filter setup, filter combination. And this time I fix Cosmos, the Galaxy template. And here I show different filter setup with different performance. And you can see that for setup E, which is 24 bands from Meta to Wise 1, 2. And what's different from the 25 bands is I exclude the flamingo J data here. And this gives the best performance in terms of outlier fraction and velocity deviation. So here I claim my best setup in my photo C is SCD template model with Cosmos and filter combination from Meta to Wise, excluding flamingo J, which gives me eta is equal to 9.27% and sigma is 0.0493. And moreover, I want to separate star from my samples. So I use, again, Lufa. There is a stellar template, and I use Pickles for stellar templates. So this time, there are 2 values, chi-square Gale and chi-square star. So chi-square Gale is the minimum chi-square value when it fits to the Galaxy template in Lufa. And chi-square star is the minimum chi-square value when it fits to stellar template in Lufa. And I will call it chi-square Gale and chi-square star later. So if chi-square Gale is larger than chi-square star, it can be possible star candidates in my samples. And vice versa, if it's smaller than chi-square star, it can be galaxies. So just to show how promising is my results, I have a color diagnostics for my data. So you can see that this red galaxy, this red data and this black data, they are the galaxy in my sample. And this green data, they are the star. You can see there are 3 clear trends in this color plotting. And just to mention, there are some blue data here and some stars, green star here. They are the spectroscopic confirmed galaxies and stars. It's also consistent with my chi-square performance. So this is the best results I can get in my NEP data. And this is the histogram of my photo. The dotted one is the data with stars. I will skip this because I don't have time. So compared with the previous results from NEP deep field, the redshift deviation of NEP deep field is 0.03, and the eta is around 5.8, but the number of sources is much smaller in the deep field. So with a larger data samples, we can reach quite good results with NEP wide field, which is quite promising. And this is a summary of my talk. And you may ask me, what are you going to do with this photo C? And actually my group is doing the follow-up research. For example, the first day speaker, Wan et al., she is doing AGN contribution with my photo C. And also one of my collaborators, he is doing cluster finding in NEP. And then also one of my friends is doing AGN contribution to local density in NEP. So that's all my presentation. Thank you.
Questions from students?
So which version of the HSC pipe do you use?
Which version?
Which version of the HSC pipeline did you use? I mean, I think previously there are indeed this kind of over-deep blending problems, but this probably are fixed in the latest version.
Okay, I think this is maybe older than this version because I just found it recently.
And you found this problem for both bright and faint galaxies?
Yes. Mostly are bright galaxies, I think.
Right, but you show the plot with megacam comparison to like 25 meg.
Yeah.
I found that difficult to understand.
You mean that this plot?
Yeah.
So this plot is HSGR minus minus is if the difference is too large, which
No, I mean the lower panel. So
lower
how deep is your megacam data?
the cam data is around 24, I think.
So then how can you use that as a truth to compare, to reject HSC sources?
Well, actually, I'm not using as a true value here. I'm just want to compare with similar wavelength here too. Yeah. So that's why I'm just excluding 3 sigma outliers and not excluding many sources.
My point is maybe you are not excluding outliers. Maybe the megacam detection is spurious.
Actually, I checked the performance after doing this is actually slightly better. So I guess I don't know.
Any more questions? If not, then think. Oh, please. Show question, right? Okay.
Yeah, so I look at the distribution. Actually, the deviation or the systematics is quite large. There's a systematic offset of point of view magnitude, and it's just it means the photometry is there's some problem. I don't know whether you aware of that. Yeah, and even I don't know what your like 1 sigma is, how big, but the Y scale is, if it's less magnitude, it's huge. So yeah, that made me wonder, is there, I don't know what issues in the photometric pipeline or how you deal with the catalog. So yeah, do you have any comment on that?
Actually, our old idea is that HSC is maybe the best data we have, and we tend to trust HSC photometry.
Yeah, but you just look at the scatter, the 1 sigma. If you compare the two, if the Y is the magnitude compared to measurement, the 1 sigma is point something magnitude, and that's I feel that's too big. Yeah. So anyway, this, if you haven't looked into this, then maybe that's something you want to think about.
Yeah. Okay, thank you. Thank you for your comment.
Okay, I think we need to move on. So let's thank James again.